So for the argon, for the pore sizes that are smaller than molecular size of argon and larger than minimum pore size, which is the helium pore size, only helium can diffuse through our membrane. And so as far as argon is, for the pore size larger than argon, both gases diffuses. So as far as the argon is concerned, the percolation effect came at work, and we can define the percolation effect as Q. So that means is a percentage of the pores that are inaccessible to argon, and just helium can diffuse through it. And if this Q, which is a function of pore size distribution, if it's larger than the threshold, percolation threshold, which is again, percolation threshold is a function of connectivity. If it's larger than that, no argon will diffuse through our system. So this right here shows different average pore size and two different pore size distribution that we have. As you can see, the percolation threshold is, for this case, for the connectivity of 6, that means 6 pores are connected to 1 node, is 25%. So for that case, you see that at 37 nanometer, 0.37 nanometer, there would be no diffusion of argon, even though that is a little bit larger than molecular size of argon itself. So we studied the effect of average pore size. We studied the effect of average pore size for permeances of gases and selectivity. As the average pore size decreases, the selectivity goes up. That's again because of the percolation effect. So that means when we use the smaller average pore size, argon cannot diffuse through some of the pores. So the permeance of the argon start decreasing more than helium, so the selectivity will go higher and higher. And the last thing, but not least, we studied the connectivity effect. So as you can see, as the connectivity decreases, the helium permeance decreases more significantly than argon. The reason for that is because we already considered the percolation effect for argon, but we didn't consider that for helium. So for a fixed connectivity, let's say 6, both argon and helium can diffuse through the system, but argon has a percolation effect. But the only way that make that percolation take into account for helium is that making some pore size to be equal to 0, or that would be equal to reducing the connectivity. So that's why the permeance of helium decreases faster than argon, and so the selectivity also decreases while the connectivity is decreased. So I want to summarize my talk. We actually made silicon carbide nanoporous membrane by the chemical vapor deposition. We developed a model to describe the CVD process, and we also developed a Pore network model. And we're trying to help us to better understand the transport characteristic of our membrane. And currently we are trying to optimize our model for the operating condition in order to implement back our optimized condition in our experiment and get the membrane with better characteristic to be able to eventually use them in the catalytic membrane reactor for hydrogen production. So I'd like to thank my advisors, Dr. Sahimi and Improvement and National Science Foundation and Department of Energy for supporting this project.
Questions? Have you done any helium leak test? And if yes, what is the leak rate?
Leak rate?
Yeah, leakage rate. Helium leak.
Leak from
The membrane. I mean, the pore sizes that we were talking is that helium passes through. So what is the leak rate?
leak rate. You mean the permeance? The permeance is in the order of 10 to the minus 7 in the cyanide.
Thank you for your impression.
observed that you have all three components in the same work. That's just from you, or is it two, three different schools involved? The
It was
experiment and the two types of modeling. All
actually it's me and there was another graduate student who graduated. I mean, we were working together. Yeah, but
that's
it
very
was
nice to have all those in one work. But the question I have is this. You mentioned that one of the simulations you did for the flow was connectivity of 6. Was it just sort of in the model simulation that's a fixed number, or is that the average of a probability distribution of connections?
you mean the connectivity?
Yeah.
It's not the, we try to, is one of the parameters that we,
No. Question is this.
Okay.
In the model, all connectivities, no matter where they are always 6, or is it that 6 is the most probable or average value?
it's
of
always
distribution?
6.
Okay.
Either always 6 or...
So it ends up being basically a very regular layer.
Yeah, exactly.
All right, well, let's thank Rayan again. Thanks, Rayan. So our next talk, Zach Leland. Zach is from Mourhatch's lab. He's going to be talking about pond dots.